Welcome to everyone, and good day to you all. My name is Jim Haldeman, and I'm the Business Development Manager for Instrumentation at the Lesman Instrument Company. Thank you for joining us for our webinar today, entitled Advanced Insights into Clamp-on Flowmeter Technology. We are fortunate to have as our presenter today, John Accardo. John is a pioneer in the field of clamp-on ultrasonic flow metering. John currently serves as the application specialist and technical consultant for Siemens. John joined Controllatron Corporation in 1976, early in the development of this clamp-on flow measurement technology. John started as a bench technician. He's had several positions technically, including senior field engineer. He's been a technical writer, technical services manager, and senior application engineer. His technical support duties have taken him worldwide, flying more than 2 million miles in support of clamp-on ultrasonic flow meters, while at Controllatron and currently with Siemens, following Siemens' acquisition of Controllatron in the year 2006. This webinar will be recorded for posting on the Lesman Instrument Company website. If you have questions, I will be monitoring the question queue. So if you have an immediate question, please enter your question there, and I will ask them on your behalf, or simply wait and we will have a question and answer period at the end of John's presentation. John, please begin your presentation.
Hi, everybody. Just want to check that you can hear me okay?
Yes, we can hear you fine.
Okay, I had to switch over to my computer audio. My headset is wanting to give me trouble, so as things would happen. Okay, thanks for that introduction. I guess that kind of covers my my life experience with clamp-on flow meters. Today's webinar will more or less delve into a lot of the history of clamp-on flow meters and where Siemens is today and where it came from, and through the development of the product over the years. And so just to kind of show how old I really am, I figured we'd start with a throwback to a long ago time and one of my favorite programs as a kid. So for those of you that are familiar with the Rocky and Bullwinkle show and Peabody and Sherman, we're going to start off with the Wayback Machine. Where are we going today, Mr. Peabody? Well, we're going to go to the Leiden, Netherlands, and we're going to set the Wayback Machine to 1621, where it all began for clamp-on flow metering. We're going to pay a visit to, amongst other people, Willebrord Snell, the mathematician, and some of the other people that have had a significant influence on clamp-on flow metering. So starting with Snell, back in 1621, he developed the law of refraction based on some previous work that was done by Ptolemy and Sol even before 1621. And the law of refraction has a very profound effect on the clamp-on ultrasonic flow meter. So little did he know in 1621 that his work was going to influence a whole industry of flow metering many, many centuries later. The law of refraction influences not only the design of the transducers and the use of Lamb wave technology, which we'll talk about in a second, but also for predicting the sound angle through a fluid flowing through a pipe and actually the physical spacing of the transducers on the pipe. Another major contributor is Osborne Reynolds, who developed the Reynolds number definition of fluid flowing through a pipe. whether it's in a laminar condition or a turbulent condition or the dreaded in between, the transition region. And also how that requires various amounts of compensation depending upon what the viscosity is and what the ultimate Reynolds number is. Christian Doppler, who we won't be talking too much about, but he discovered the Doppler effect, the Doppler shift, and how the relative motion of a source and an observer can affect the observed frequency. So in other words, you can tell the velocity of something by its relative frequency relative to the observer. His Doppler effect theory is effective in Doppler flow measurement, which we have done over the years. We're not currently doing it, but it did certainly have influence on a whole range of flow metering methodology. The next one is Horace Lamb, who developed the theory of Lamb waves and how waves propagate through plates, or otherwise known as longitudinal waves, as opposed to shear waves. Something that Controlotron Corporation developed right from the very start of the ultrasonic clamp-on flow metering business, and why that methodology is so far superior to shear wave. And then lastly, Joe Baumel, or JB as we called him, was the founder and president of Controlotron Corporation, created the first clamp-on ultrasonic flow meter back in 1973. I came on board in 1976, so I've been there for quite some time working on these things. Joe, last check, is still active in patenting various techniques for clamp-on flow measurement and other types of flow measurement. Obviously he was the driving force behind this device, which was the first of its kind ever. So just going back a little ways, in 1972, the first clamp-on flow meter was invented and brought to market in 1973. The Model 240, which you see pictured there, was sold originally to Dow Chemical. It was the first customer that we had. Every single flow meter that we built back then and right through to the current day utilized Lamb wave techniques and Lamb wave technology, wide beam as we called it, which referred to the way the ultrasonic wave presented itself as it traveled across the pipe. So Controlotron developed and deployed the wide beam ultrasonic flow meter, transit time flow meter. It was the only one of its kind at that time, and as I said, it utilized the Lamb wave from the beginning, and that technology was patented by Controlotron. So we were the only ones that offered Lamb wave technology. In 78, the second generation Model 480 was released, which was really just a more advanced and more stable version of the 240. Both of those meters were analog, fully analog devices. Everything that was a bit of data was as an analog value. So sonic velocity was a voltage level, and transit time was a voltage level. It was all relative voltage ramps over time that gave us our numbers that we needed to create a flow reading. Every single one of these meters was also a custom product. When a customer purchased a flow meter, you think of that nowadays. If you're familiar with the clamp-on meters, you know that we require an application data sheet, which kind of gives us a look at what your application is. What are you flowing? What your pipe size is? What your liquid is, and so on and so on. Back then, we needed to know everything. We needed to know what your pipe was, what your fluid was, what flow units you wanted the meter to read in, and so on and so on and so on. And we actually created what we call the scale computer module, which was a plug-in module, and you might be able to see it here plugged into the meter, which configured the meter for the specific size pipe that you were going to measure. There was no programmability back then. So if you said you had a 6-inch schedule 40 pipe, and when you got your meter, you realized it was a 6-inch schedule 80, you didn't have a meter anymore. You had to send it back and have it reconfigured. But that was the name of the game back in 1978 and 1973. In 1984, we released the 960 meter. So if you might see a pattern going on here, each time we doubled the number. That was kind of to say, this one's twice as good as the previous one. But the third generation model 960 was the first all digital system. And so instead of discrete components configuring a circuit board for your application, it was all burnt onto an EEPROM, which was just a small handheld device that you could plug in to the system, and it would configure the system for your specific pipe size. At that time, where we did introduce energy measurement in the 480 model, in the 960 model, we actually had an all-in-one energy meter, so you can have one device that measured flow and energy at the same time. And we did our first installations on the Alaska pipeline. We were utilized as a flow switch that performed a very critical operation to monitor flow, and in the event that the flow dropped below a preset value, the flow meter would trigger an alarm that would drop a check valve and have it positioned just in case the flow pipe in the pipe reversed. It would close the valve and prevent a reverse leak in the pipe. So they were deployed up and down the entire Alaska pipeline back in the mid to late 80s. And then in 1988, the first fully programmable system was released, the model 990. We kind of broke with the numbering tradition there, but it was the first fully programmable system. It utilized universal and high precision transducers. So in 1988, we made a shift. Up until then, up until the release of the 990, as I said, every flow meter came with Lamb wave transducers. That was the only way the flow meter was delivered. And as we go through this, we'll talk about what makes a Lamb wave transducer a Lamb wave transducer. But specifically, it's fit to the pipe, more or less. It's matched to the pipe that you're measuring. When you have a programmable meter, now you kind of dig yourself a hole, because now you can take a meter and go to any pipe you want and just program the configuration of that pipe, what size it is, what kind of material it's made from, what the wall thickness is. But then you need the right transducer for that pipe. So we were faced with the dilemma of having a very easy to program flow meter and the need for a truckload of transducers. So we developed and released what we called universal transducers at that point, which were technically shear wave transducers. However, at the same time, the computing power that we now had with this programmable system lent itself to very high-end applications, such as leak detection applications. And for those, we needed the precision of Lamb wave. So we didn't disperse with the Lamb wave transducers. We kept them, but we renamed them high precision transducers. So now we had two lines of transducers, which we maintain to this day. And in fact, the 990 transducers are still in use with the FS230 system that we have now as the high temperature transducers, because they're all metal construction and they're much more stable under varying temperature conditions, under very high temperature conditions. So along with this 990 release, we basically reinvented the wheel. We had a meter that we could now program. We had high-end systems such as standalone leak detection systems. We introduced reflect transducer mounting. We had our first dual path systems, and we used a phase-based measurement system using a multi-pulse transmit for the first time. Prior to that, we used more or less a single pulse transmit. 990s were installed worldwide. I traveled to the far corners of the earth supporting the 990s over the years. and they were introduced to many hydrocarbon pipeline systems around the world. In 1998, the 5th generation system, which is really about the 12th generation system when we look at the sub-generations of each of the previous ones I covered, but the Model 1010 was released. And the Model 1010 was really the most versatile clamp-on flow meter ever. And you can arguably say it's the most versatile flow meter ever. It was available as a dual path system, single path system, 4-path system, 4-channel system, dual channel energy system. The first natural gas clamp-on flow meters, transit time, were introduced in the 1010 program. The first interface detector, or as some call it, the clamp-on gravitometer. The introduction of digital signal processing, and which enabled us to do gas measurement. Multiple types of communication protocols were introduced. It had a full graphics display. It was capable of doing standard volume measurement and had the full alphanumeric keypad, which was more or less the same as the 990 in that regard, although the 990 used a handheld programmer. With the 1010, it was built right onto the front panel of the machine. The 1010 was in production for over 20 years. There's thousands and thousands of them in service worldwide. Every day we take tech support calls on them. There's still just a ton of them out there in the field, still working away. In 2006, Siemens acquires Controlotron. The Model 1010 remains in production, and then ultimately it was further engineered with the release of what we call the version 5 system for additional performance and versatility improvements. Switching from Controlotron to Siemens in 2006 was kind of seamless. My job, from my standpoint, didn't change one bit. It was just a different name on my desk. That was it. But the flow meter remained the same. The color changed a little bit to match Siemens protocols, but other than that, it was exactly the same flow meter. It just said Siemens on it instead of Controlotron. In 2017 through 2020, the first models of the FS230 system were introduced. This was the first meter that was fully engineered by Siemens. There was obviously a lot of old Controlotron personnel involved in the development, but under the Siemens banner, this was the first release of a fully Siemens designed flow meter. Along with the FS230 came a dual path as standard. 4-path with a remote DSL was available, and obviously not was available, is available. An all-in-one hydrocarbon liquid meter, a natural gas meter, class 1 div 1 enclosure with remote DSLs. It brought 100 hertz update rate, long cable runs, much longer than we were able to do with the previous generation systems. And that was made possible through the use of a SSL cable to the remote DSL, so that the actual transducer cables can be very short, and then all the data gets transferred over an Ethernet cable back to the transmitter, which is much more noise immune and is capable of much longer cable runs. The FS230 brought built-in programming wizards. It was a direct replacement for the aging 1010 and even 990 flow meters, if people still had them in service. So it's literally a device that you can unplug a 1010 from the wall, bolt up the 230, reconnect your transducer cables, and off you go, because it utilizes the same transducers. So it's capable of supporting both 990 and 1010 transducers. Those are the mainstream transducers, or those are the transducers that the FS230 is supplied with. They've just been relabeled as FSS 200 transducers, but they are the same transducers. And of course, along with that, it brought the safety approvals and agency approvals that we had with the prior generation systems. And we also introduced recently an ultra low power standalone DSL, which can be programmed via PDM and uses less than a watt when in service. Okay, so that's what led up to where we are today. But what hasn't changed is the fundamentals of all transit time flow meters, regardless of who makes them. And like I said, when I started with Controlotron in '76, only we made them. But now there's many people, many companies out there making transit time flow meters. And the fundamentals are all the same. You have two transducers on the pipe, and an ultrasonic wave is sent from one transducer into the pipe wall, then through the fluid stream, through the other pipe wall to the receiving transducer. And that goes in both directions. So one transducer is a transmitter, the other is the receiver. One sends a sound beam to the other, and then they reverse roles. And what was the receiver now becomes the transmitter and sends a signal back the same exact way, same direction, same path length, same frequency, same everything. But what happens is when fluid is moving in the pipe, the effect of the fluid velocity works to accelerate the sonic beam in one direction and delay it in the opposite direction. And as a result, there's a net time difference. So what you see on the right now is the two transmit signals shown synchronized together, even though they're happening alternately. They're not happening at the same time. But they start out synchronized to one another, but you'll see to the right, the receive signals are shifted from one another. Now, if there was no flow in the pipe, they would be perfectly aligned with each other because it would take exactly the same amount of time to go one way as the other. But when there's flow moving in the pipe, the signal going downstream is accelerated by the flow, and the signal going upstream is delayed by the flow. And as a result, there's a difference in time between the two signals. That difference in time, which is known as delta T, is related to the speed of, or the velocity of the flow moving in the pipe. So technically, the flow meter is a speedometer. It's just measuring flow velocity and then ultimately converting that velocity into a volumetric rate of your choosing. It's also interesting to note that back in the day at Controlotron, when we had a softball team, that was our name, the Delta T's. So I thought you'd like to know that. But in any case, you have a transit time downstream and a transit time upstream, and that difference in time is due to the flow rate. Now, this is the fundamental way that all clamp-on transit time flow meters work, regardless of who makes them, but how you accomplish it is what sets things apart. The method for accomplishing this measurement varies somewhat from manufacturer to manufacturer, and there's a number of factors that influence what occurs in the process. So we're going to take a look at how Siemens handles those changes and what we've done over the years to pioneer some of these measurement techniques and what sets us apart from the competitors. So we started with Snell. Let's continue with Snell. So if we have a couple of questions here about how does Snell's law impact the clamp-on flow meter, one question is, how is the distance between the transducers determined? And second question is, how can an ultrasonic meter maintain accuracy under variable liquid conditions? And the answer is Snell's law of refraction. So basically, Snell's law says that when an ultrasonic wave passes through an interface between two materials, two different materials, at an oblique angle, and by different, the two materials have different indices of refraction, which in the case of sound is two different speeds of sound, sonic velocity A and sonic velocity B. When the sonic beam or the wave passes through that interface, it produces a reflected signal and a refracted signal. And the refraction takes place at the interface of the two materials. So the effect of Snell's law occurs in two places. It occurs at the interface of the transducer and the pipe wall, and it also occurs at the interface of the pipe wall and the fluid stream, because again, that's another difference in density and sonic velocity. So in this drawing on the left here, you see a sonic wave being introduced to a pipe wall, represented by the horizontal line, and then there's a refraction where that sonic beam changes direction in the pipe wall. If we were then to look at this again and say above the horizontal line is the pipe wall and below the horizontal line is the fluid, the same thing is going to happen again. You're going to have the sonic beam traveling in one direction in the pipe wall and changing direction in the flow stream. And the amount that that sonic beam changes direction in the flow stream is relative to the speed of sound of the fluid that we're measuring. And that's a variable. Fluid can change speed of sound due to pressure, due to temperature, due to the liquid chemistry. And so think about an application, say on a hydrocarbon pipeline, where you might be flowing gasoline one day, and then later on you're flowing diesel fuel, and in between you're flowing jet fuel, and then maybe some fuel oil. That represents quite a range of speed of sound. And so that refraction angle is going to change with each of those fluids. And it's critical for a flow meter, a clamp-on flow meter, to maintain its accuracy, to be able to detect that change in beam angle, determine what it is, because it's used, that angle is used in the calculation of flow. What you can also see on this right picture is the transducer sitting on the pipe, and you see that arrow in the pipe wall pointing straight down the axis of the pipe. That is what we call axial beam injection, and that's through the calculation of Snell's law relative to the pipe material, which in this case would be a steel pipe. And so the design of the transducer is influenced by this law from back in 1621 to ensure that when it enters the pipe wall, it refracts to 90 degrees and travels down the pipe wall, and using the pipe as a waveguide, using its natural waveguide property. And that will conduct the beam over a very large area and radiate energy into the flow stream over a very large area. Hence the term wide beam that we developed back at the beginning of the flow meters in 1973. Now, the other thing you might see here in the right side is the gas sonic velocity and the refraction angle for gas. And it's much, much steeper, much closer to the normal. And that's because the speed of sound of gas is so much slower than that of liquid. It's about a fourth of what water is at a given temperature. So again, that changes the position of the transducers. So the meter, when you program the meter, you tell it what your fluid is. And from that information, the meter has a rough idea of what the speed of sound should be. And it uses that information to calculate what the transducer spacing will be so that it intercepts the refracted sonic beam. What is a benefit of having a wide beam is that even if you're not perfectly positioned, you still have plenty of energy surrounding the transducers, and the meter is able to find the receive signal and measure the correct speed of sound and know what the refraction angle is. So the wide beam is critical, excuse me, to being able to operate when the speed of sound is changing so that you do not lose the receive signal at any time. So if we look at waves, what's the benefit of Lamb wave technology? If you look at the Lamb wave on top as a longitudinal wave, the beam gets injected into the pipe and it turns to 90 degrees. It turns to travel along the pipe and uses it as a waveguide. So it's traveling down the pipe wall, and it's literally like if you were to take a hammer and strike the end of the pipe. If you had the pipe square cut, you hit the end of the pipe with a hammer, it would push sound waves down along the pipe wall. And so the pipe signal will travel way down the wall, well past the receiving transducer, and just keep on going. Whereas a transverse or shear wave comes in at an angle, but it doesn't refract to the 90. It refracts, of course, but it's sort of hammering up and down in the pipe. So its movement is an up and down movement as opposed to a longitudinal movement along the pipe. What I often use as an analogy of this is if you think of going to a baseball stadium and doing the wave. Let me go back. Sorry. If you were, when you see the wave go around the stadium, people are standing up and sitting down, and that propagates around the stadium. That's a shear wave, a transverse wave. If people were sitting in their seats and leaning into the person next to them, and that person leaned into the person next to them, that would be a longitudinal wave. So the wave would still propagate in the same direction, but it would do it in a different fashion. Also, if we look at the sound velocities down at the bottom of the screen there, you'll see that the longitudinal wave travels a lot faster than the shear wave does down the pipe because of the method that it utilizes. So let's see what that benefit is. If we look at a shear wave at the top of the screen here, you see that the beam, you see the outline of the transducer, and you see the beam angle that's traveling into the pipe. And then there's a refraction that takes place, but it does not turn to the 90. It refracts and then it starts rattling its way down the pipe wall. So it's bouncing down the pipe wall. And the issue with that is that when that wave reflects off the inner wall and comes back up, it's not necessarily in sync with the wave that's arriving at that point from the transducer. So if you think of a transducer wave as coming in, when that wave arrives at the pipe wall, that reflected wave inside the pipe wall isn't necessarily combining with it. It may be clashing with it, as a matter of fact. And so you get a dispersive wave. So the propagation down the pipe wall is a very noisy one. And you could see multiple wave fronts on the right side, and you see this cross-hatching pattern in the pipe wall. And so it disperses as it travels down the pipe wall. And the shape of it varies depending upon where you pick it up. If we look at a Lamb wave, the beam comes into the pipe at a predicted angle where we know it's going to refract to the 90 and travel down the pipe wall. And that's going to cause the pipe to vibrate at the normal, vibrate up and down, and transfer that energy into the flow stream. That wave is going to be very coherent. It's non-dispersive. And so it stays constant as it travels down the wall. If you look at the right side of the screen, you see the wave fronts are nice and evenly spaced, very coherent. And in the pipe wall, you can see how they're perfectly vertical and evenly spaced. There's no disruptive wave pattern in the pipe wall. And if we look at what that does to the receive signal, well, and before I say that, what the real benefit of a Lamb wave transducer is, and why it's so profoundly superior to shear wave, is that when you use Lamb wave technology, the pipe is actually part of the transmission mechanism. So you're actually exciting the pipe wall. You're just giving the pipe energy and letting the pipe do the work. And so to get a Lamb wave, you've got to match two characteristics. One, you've got to match the phase velocity of the material that you're injecting the energy into. So you're, in this case, a steel pipe wall, you're matching its phase velocity or its speed of sound. But the second level is you want to match the resonance of that pipe wall, which is relative to its thickness. So if you think of a guitar string, the sound it makes is relative to how thick it is. And that's basically what the pipe wall is. It's a guitar string. And so what we want to do is we want to resonate that guitar string at its natural frequency. And so what we're doing is we're giving the pipe exactly what it wants. It's the pipe that dictates what it needs, not the transducer. So competitors will say, well, here's a transducer, you stick it on your pipe and you go. But you're not matching the characteristics of the pipe. The pipe is what determines what it needs. It knows what frequency it wants because that's its resonance. And also the material that it's made from determines what the phase velocity is. So the pipe is the transmitting mechanism. With a shear wave, the pipe is an obstacle. It's just something that's in the way that you've got to get a signal to get through in order to get your flow measurement. And so if you don't resonate the pipe at a frequency that it wants to resonate at, it's not going to produce a very good signal, both in terms of shape or quality and amplitude. So in order to get a signal to get through it, you've got to hit it harder. And so many of our competitors' meters use very, very high voltage transmits, 100, 200, 300 volts in some cases. So you just hit the pipe with a sledgehammer and it makes enough noise to get a signal to get across the pipe. So it's really how you go about getting the signal to get into the pipe and to get something that you can work with that is going to be predictable and stable. So the key is ultimately the received signal quality and how it is affected by changes in the application, such as temperature, pressure, flow velocity, and fluid type. And we can see kind of an example of that here. At the top, you see a dispersive wave, and as it travels down the pipe wall, it's changing. Whereas on the bottom is a Lamb wave, a non-dispersive wave. And as it travels, it stays exactly the same. So the wave that it's injecting into the pipe wall, regardless of where it's emerging from the pipe, is the same. So think about what I showed you earlier with Snell's law, with the refraction angle of the sonic beam relative to the fluid. If you have your transducers on the pipe and your fluid changes, that means your refraction angle changes. That means the position of where the signal is arriving at the received transducer has changed. And if you have a dispersive wave, that means that that wave shape is now changing. But it's changing in one direction versus the other direction. And when those two don't match up, you get shifts in calibration, shifts in your flow reading. So that's what's so critical about the Lamb wave technology, and why others waited for the patents to run out so they could utilize that technique. The Siemens Lamb wave versus shear wave transducers. Yes, we do make shear wave transducers. And as I said earlier, with the 990, we introduced them so that we could more or less pop onto any pipe we wanted to and just program the meter for the particular transducers. But there is a difference. So Lamb wave transducers, or what we call high precision sensors, are designed to match, as I said already, the pipe's resonant frequency and the speed of sound of the pipe. They use an injection angle that matches the pipe's incidence of refraction so that it utilizes the pipe's waveguide properties. But a second level step is that they're tuned to the pipe's frequency, and we let the pipe dictate that. And that's because every flow meter we've made since the beginning of the 990s runs through a frequency sweep when you first install it. So each transducer, even though it's a high precision, can be operated at its own center frequency or a primary harmonic of that center frequency. So the meter will test the range of frequencies each transducer is capable of and let the pipe tell us which one it likes. And that's done when you hit the resonance, you're going to produce the strongest signal. And so by identifying the strongest signal, we know which frequency works best with that pipe, and we utilize that frequency. So these characteristics produce the coherent Lamb wave signal, which remains independent of the process conditions. And so even though application conditions are changing, the meter is able to maintain its accuracy. One of the conscious decisions we made back in the day when we introduced them for the 990 was that they're for steel pipe only. As I said earlier, the first 3 generations of flow meters, all we used was Lamb wave. And so there were many different types of transducers depending upon what your pipe was made out of. When we ventured into the high-end applications with the 990, we decided to continue to use the Lamb wave, but rather than make them for copper pipes and ductile iron pipes and copper nickel pipes and so forth, we just brought back the ones for steel pipe, because those are the most applications that require high degrees of accuracy are in steel pipe. Applications such as gas pipelines, hydrocarbon pipelines, those are all in steel pipes. You won't find a cast iron hydrocarbon pipeline. And so that was a decision that we made. And even though we do have the capability of making Lamb wave for, say, a copper nickel pipe, we don't do it. On the other hand, shear wave transducers, or what we call universal sensors, match the pipe's resonant frequency or a harmonic of it. So they don't necessarily match the phase velocity, but what we do, which is different from everyone else, is we still do that same frequency sweep. So we tune the transducer to the pipe's natural resonant frequency. The design of the universal transducers is to utilize an injection angle that allows it to be used on all pipe materials. So you can use it on steel pipe if you want. You can use it on everything else, ductile, copper, you name it, plastic pipes. And interestingly, what you might not know, or maybe you do know, high precision sensors can be used on plastic pipes. And the reason for that is you don't get the resonance. You don't get resonance and you don't get the Lamb wave travel in a plastic pipe that you do on a metallic pipe. So you can, in fact, use high precision transducers on a plastic pipe. Even though they're not specifically matched to the pipe, proper selection of the universal transducers will ensure the best quality signal and match to the pipe that you're trying to measure and produce an accurate flow measurement. So how would you go about doing that? Well, if you're familiar with the Cyware tool or the replacement for the Cyware tool, which is the FS200 utility, that can help you pick what the best universal is for your specific pipe. Generally, universal sensors are picked based on pipe diameter, but the wall thickness still has an impact because the wall thickness determines what the frequency, the resonant frequency of the pipe is, and so it plays into the game of choosing the best universal transducers for the pipe. On the HP side, those transducers are selected based on wall thickness. Diameter doesn't play into the game at all. So whatever the wall thickness is what determines what the right high precision transducer is. One of the things that sets us apart from other manufacturers is this fact that we tune our transducers to the pipes by doing these frequency sweeps. Other manufacturers tout that they have Lamb wave transducers as well, but none of them do the frequency sweep. They operate at fixed frequencies. So even though you have a Lamb wave transducer, it doesn't mean you're going to get the ideal waveform on the pipe if you're not matching the resonance of the pipe. And it's very easy to demonstrate how most of the time you're not operating at the primary frequency of the transducer. You're operating at what the pipe likes, and it doesn't necessarily match up with that transducer's primary frequency. It's a primary harmonic of the frequency. But if you stick with just the transducer frequency, chances are you're not going to pick the best frequency for the pipe that you're on. So switching gears, Reynolds number is another impact that all flow meters have to deal with. Reynolds numbers determine the flow profile of the fluid traveling down the pipe. And one of the things that, well, basically, Reynolds number was developed by Osborne Reynolds, and it's based upon the dimensions of the pipe and the fluid viscosity, what shape the fluid takes on as it travels down the pipe wall. And it actually impacts the correction factor that the flow meters need to apply in order to maintain an accurate measurement. So if we look at the different regimes of Reynolds number, there's basically laminar flow and turbulent flow. And then in between, there's the dreaded transition flow. Now, one of the things that a lot of people that I know that I encounter out in the field think that, oh, you guys want laminar flow conditions. And that's not true at all. But I think that's from a misunderstanding of what laminar flow is. But laminar flow is basically if you have a viscous fluid or you're at a very low flow rate, the fluid just travels down the pipe in layers or lamina. And it's a nice smooth condition. But as you increase flow, or if the viscosity is lower, those layers break down. The friction between the layers starts to cause turbulence, and the fluid starts to tumble and spin and travel down the pipe in a turbulent fashion. And the majority of the applications that we see are in fact in the turbulent flow regime. But we don't care. You can be laminar, you can be turbulent, doesn't matter. The meter will correct for it. In between the two, and this is all determined by a number, and the number is just a calculation of the viscosity, the ID of the pipe, and the flow rate, and to some degree the roughness factor of the inside of the pipe. And that results in a number that's dimensionless. Typically, if that number is less than 2300, it's deemed that the flow is in a laminar flow condition. If it's above 4000, it's in a turbulent flow condition. And if it's in between those two, you're in transition. And transition is just a combination of laminar and turbulent. But the reason I call it the dreaded transition region is because it doesn't hurt the flow meter at all, but it will impact any flow meter's accuracy because it's unpredictable. The definition of transition is there's no definition. So you really don't know how turbulent you are and how laminar you are. And so you're trying to apply a correction factor, and we do apply a correction factor in the transition region, but you don't know how perfect it is. You never really will know. So you can see a departure from your accuracy while you're in transition. And it's not ridiculous, but it could be ridiculous, but it generally isn't. It's just a couple of percent. But what would be ridiculous is if you put in the wrong viscosity number and the meter thought you were laminar and you were really turbulent, or vice versa. Then you could see upwards of an 18% flow reading error. Okay, so knowing your viscosity is important. Again, when you pick a liquid, it plugs in a default viscosity. But if you have an application where viscosity varies, well, you need to know what that is, and we do address that. And I know I'm really taking a long time here, so I'm going to try to move it along as quickly as I can. So also, another thing that we see in the field is disturbed flow profiles. And disturbed flow profiles are due to limited straight run of pipe. When there's limited straight run of pipe because there's an elbow or a multiple elbow or an expander or a reducer or some other pipe geometry, it affects the way the fluid travels down the pipe. There's an old rule of thumb that says, well, when you install a flowmeter, you should have 10 diameters of straight pipe upstream and 5 downstream. Well, back in the early 90s, well, actually before that, we were seeing applications where we were getting enhanced errors for no seeming reason at all. There was 20 diameters of straight pipe and we should be in perfect shape, and yet the flow meter was reading incorrectly. And so Controlotron was one of the primary sponsors of a research project done at the NIST in the early 90s that measured the effects of differing pipe geometries on flow profile. And the results of those tests were that it was determined that the traditional 10 and 5 rule isn't always ideal. It all comes down to what is upstream. How many elbows are there, and how are they relative to one another? Are they in plane with each other, out of plane with each other? Is it a T? Is it a reducer? All of those things have impacts that are long lasting, that can last considerably longer than 10 diameters. And so as a result of these tests, Controlotron developed what we call the pipe configuration tool, or what's been renamed the disturbed flow tool, and I think it's been renamed again straight run conditions or something like that in the menu. So all of these things I've been covering up till now are some of the problems that we face in the field as a clamp-on flow meter. And we have ways to mitigate these things. So looking at some of the things that we're up against, we have limited straight run of pipe, which I just talked about, non-axial flow conditions, multi-product flows, bidirectional flow, product identification, beam blowing with gas applications, and high accuracy requirements. And maybe all of these things in one application. Being able to handle that is a key part of how good your flow meter really is. So keeping on the theme of the disturbed flow tool, if we look at the graphic in the upper left here, you see a flow coming around an elbow, and you also see a circle there where it's looking down the pipe end on. And that flow profile is anything but what I showed you earlier with the Reynolds number. You have 2 high velocity components, and it's not axial. It's not coming down straight along the pipe walls. It's at an angle to the pipe walls. So this is where the information from the studies at the NIST came into play, and where our straight run tool or disturbed flow tool came into play. Something that Controlotron pioneered and developed and deployed back in the 990 program, and it's been in every flow meter since, and it continues to be in the FS230. And it's just simply a matter of picking your flow condition. What is your pipe geometry? In the menu, single elbow, you have double elbows in plane, double elbows out of plane, reducers, expanders, and how far away they are. And by doing so, you see on the right flow profile correction curves that are variable, that are a function of data that you've entered to correct for the actual flow profile condition. So that gives us the ability to work with limited straight run and still maintain a high degree of accuracy.
John, we did get a question here, and the question was, is this pipe straightening feature a standard on this Siemens product? And the answer to that question is yes. Go ahead.
In every meter, including the 220 meter. So all flow meters that we've made since we introduced this in the 990s have this built in. And that's no different in the 230 and the 220, they both have it.
Thank you.
You can even see the menu screen, 2.1.3.2. So it's in the setup section of the menu. So again, this was all Controlotron, along with some other companies, sponsored this research done by a Dr. Mattingly and a Dr. Yu at the NIST. I think they published a report in '93. So another thing that we do to help mitigate disturbed flow profiles is multi-path flow measurement. So you see on the left, dual path, and on the right, quad path. So the ability to have 2 pairs of transducers installed on the pipe or 4 pairs of transducers, and reflect mode. So a dual path and reflect mode is basically 4 traverses across the pipe. So you get a lot more signal averaging. And so between the multiple paths and the reflect mounting, you can counter 2 effects. One is an asymmetric flow profile, because what will happen many times is that if the flow profile is asymmetrical, the sonic beam may miss the high velocity component. So if, say, the high velocity component is over here, we're not seeing it with a single path, maybe not even with a dual path. But in fact, I know one competitor of ours says, oh, well, you don't need multiple paths. You just move your transducers around the pipe until you find the highest flow reading. And that's where you go, because that's where you get the right average. And that's something we've been doing since the 480 days. We used to call it a rotational test. But the problem is that you're swirling. So that high velocity component is moving around the pipe in circles. And so by having multiple beams, the probability of seeing it increases. So it's going in one beam and then out in one beam and into the other beam and so on. And so a properly operating multiple beam system, you'll see the paths mirroring each other. When one path goes up in reading, the other path goes down in reading, and vice versa. And so the average stays constant.
John, I'm just going to interrupt for 1 second and just let our audience know that we are running a little longer than we anticipated because of John's in-depth discussion. So if you want to stay on, please do. If you feel you need to sign off to go to your next meeting, that's fine as well. We will continue to record the presentation. You can always come back and watch it, but we're going to keep moving. Thank you.
Yeah, sorry, I put all this together, but rehearsing it is trying to keep it to 45 minutes was a real challenge, but I'm trying to move it along here.
No problem.
Okay.
Like I said, John, it's being recorded, so people can always come back. Okay.
All right, thanks. So anyway, looking at this combined with the next slide, we see transducers mounted in reflect. And you see the sonic beam angle traveling across the pipe and back. And any flow meter, any transit time flow clamp-on flow meter has to, by nature, assume that the flow is axial, because it has to calculate the refraction angle in order to be accurate. And so when you have an axial flow, if I'm in reflect mount, I know what my refraction angle is because I've measured my speed of sound, and I can compute what this angle is, what the angle of the sonic beam is relative to the flow direction. And this is regardless of whether you're in direct mount or reflect. So if I was in direct mount, this transducer on the right would be down on the bottom, and I would just have one traverse across the pipe. But in reflect mount, you could see that the angle here and the angle on the right side would match. And this is no different than an airplane flying through the air. If it has wind on its nose, it's calculating its airspeed based upon the angle of the wind. And so you need to know that angle. If that angle is wrong, your flow measurement would be wrong, or your airspeed indicator would be wrong. So this is why we want straight run of pipe, because if you have a long straight run, the flow is axial. It gets back to becoming axial after a certain amount of pipe diameters, and it's parallel to the pipe walls as you would expect. But if you're relatively close to pipe anomalies, you can see crossflow conditions. So here's a crossflow condition. And so now the flow, and this is a little dramatic, but the flow is traveling at an angle relative to the pipe walls because it came around an elbow, and now it's not propagating axially down the pipe. So the speed of sound of the fluid is still the same. So the meter is still calculating the same beam angle relative to the flow, which means it's wrong. So you could see what the expected angle is and what the meter is computing, but you could see what the actual angle is on the left, and that's going to produce an error, and an error of sizable proportions. And if you were in direct mount, you would be in a big error condition because there's no way of knowing otherwise that you're seeing a crossflow condition. And this is one reason why a clamp-on meter has advantages over a wetted meter. People will think that, oh, well, if I have transducers inserted through the pipe wall and touching the fluid, that's a more accurate measurement. And that's a better way to measure. And it's absolutely not. A clamp-on meter will only need half the number of transducers of an insert meter because an insert meter is always in direct mount. So this error would affect an insert meter, and unless they put the same number of transducers pointing in the opposite direction, they're going to have a big error. So a dual path clamp-on meter would be the equivalent of a 4-path wetted meter. So they would need 4 sets of transducers. A 4-path ultrasonic clamp-on meter would be the same as an 8-path wetted meter.
John,
so the advantage of being in reflect.
We do have a question. Are the transducers interchangeable, or is only one downstream and the other upstream?
They're interchangeable. They're just transducers until you put them on the pipe. And then just by nature of their position relative to one another, one is the downstream and one is the upstream. Okay, so having the transducers in reflect mount, and this is the primary benefit of reflect mount. The error that you see on the left side of the screen is offset by the error on the right side of the screen. So the error, the actual angle that we get on the one side is offset by the actual angle on the other side. So they cancel one another. And as a result, a large error, an error that's potentially 4% for every 1 degree out of plane that flow profile is, gets reduced to essentially nothing because of the averaging of the 2 paths. I'm losing my tongue here. Reflect mounting not only gives you better averaging of the flow stream because the sonic beam spends twice as much time in the flow stream, but it gives you that reverse angle correction, and that will cancel out effects of crossflow. So combined with multiple paths, reflect mounting, and the flow profile tool, you can significantly minimize or eliminate the effects of limited straight run of piping. Okay, so another application that's very common to us is multi-product pipelines, hydrocarbon pipelines, which flow many different fluids in the same pipe at different times. And so here's a chart that shows a typical range of fluids well, not necessarily every fluid would be in every pipeline, but a typical range of hydrocarbon fluids that we might see, starting from MTBE at the bottom all the way up to heavy fuel oil. So from the lightest to the densest. And what this chart is showing is the speed of sound of each of those products at different temperatures. Now, what our hydrocarbon meter does, amongst other things, it identifies what product is in your pipeline. But then it also has to correct for that particular product. Now, each of these products has a different viscosity value, has a different density value. And in most cases, when you're measuring flow in a hydrocarbon pipeline, you want normalized flow. You want, or what is known as standard volume flow. So you want to correct the flow to what it would be at 60 degrees Fahrenheit, so that you're always comparing apples to apples. And that's a function of the fluid density and also the temperature. And the way that we identify a fluid is by its speed of sound. The speed of sound is its signature. But look at this chart. Suppose that my meter was measuring a speed of sound of 1400 meters per second. If I was to say to you, well, what fluid am I flowing? I just shrug my shoulders and say, I don't know. There's a whole bunch of them. It could be any of them. It could be kerosene, it could be fuel oil, it could be gas, it could be diesel. There's no way to know. The only way to know is to say, well, what is the speed of sound and what is the temperature? And then normalize that temperature to 60 degrees. So if we do that, then there's no question as to what fluid it is. It's what is the speed of sound. If I'm measuring 1400 meters per second and I'm at 60 degrees, what fluid am I seeing? It's low sulfur diesel, and it's unmistakable at that point. And so that's what a hydrocarbon meter will do. It will identify product through what we call a liquid table. And here's a liquid table. This is the 230 version. It's a little bit different than the 1010 version in some ways. It's identical in every way except that there's no product names. There's just identifiers. But what you see in the left column here are speeds of sound. But they're not called speed of sound. They're called liquidant. And that's because it's a speed of sound corrected to 60 degrees Fahrenheit. What you might notice from the chart on the left is that as temperature goes up, the speed of sound of each of these products gets lower. It goes down. But they all follow exactly the same slope. Thank goodness, because otherwise we wouldn't be able to do this. So they all change at a rate of 2.3 meters per second for every 1 degree Fahrenheit, or 4.1 meters per second for every 1 degree Celsius. So by knowing what the temperature is, and by knowing what the actual speed of sound is, we can use that slope factor to calculate what that speed of sound would be at 60 degrees and positively identify that liquid. And so what each entry in this table on the right is the speed of sound at 60 degrees for a range of products, and what the viscosity is and what the density is at 60 degrees for each of those products. I should correct myself there. It's what the density is at 60 degrees, but it's what the viscosity is at two differing temperatures, which allows us to calculate what the viscosity is at any temperature. And so what the meter will do, it will measure the actual speed of sound of the product. It will correct it to 60 degrees. It will then go to the lookup table, find out what liquid it is, determine what the density is at 60 degrees so that you can do standard volume correction. It will also determine what the viscosity is at the current temperature. So it's calculating the correct Reynolds number, which remember is a function of viscosity and flow rate. And so even though you could have different products in the pipe, the meter can identify them and do the corrective action to give you accurate measurement, regardless of what that liquid is. Now, without Lamb Wave, And without that wide beam, it might not be so easy to do this, because each time one of these products changes, the refraction angle of the sonic beam changes. And if your transducers weren't well matched to the pipe, your wave shape would change. And so you could have a meter that was accurately measuring flow for one liquid, and then you switch to a different liquid and suddenly your accuracy is not so good anymore. And that's because your wave shape changed. So it really, Lamb wave, and of course Snell's law going back to 1621, all play heavily into being able to do this kind of work. So let's look at tuning the transducer. And again, on the right, you see that same graphic I showed you earlier about a dispersive wave and a non-dispersive wave. One of the nice things about the graphics display on the 1010 and now on the 230 is that you can actually see your transducer waveform. And on the waveform on the left is a proper wave shape. You can see that there's a flat line to the left, and then there's a gradually increasing sine wave, which is the arrival of the sonic beam at the receiving transducer. And if you look really, really closely where my mouse is, there's an X, and that's identifying the first cycle of the waveform, or the arrival point of the waveform. And that's arrived at through the wave shape by predicting the slope angle of the front end of the wave. Where it crosses through zero, we can identify the arrival of the received signal very precisely. And that wave will not change. So if you change your fluid in your pipe, and now you had say gasoline in your pipe with a speed of sound of 1250 meters per second, and now you have diesel fuel with a speed of sound of 1370, your signal is going to arrive later in time because the speed of sound is slower. And all that's going to happen is that received signal is going to move, like you see on the bottom on the right, but the shape won't change. So we can maintain the measurement without any sacrifice of accuracy. If you're not matched to the pipe, or if you're using a shear wave, you can get a very poor quality wave shape, and you end up with a dispersive wave. And as that signal moves, the shape changes, and you can see it spreading out at the top there. And now your calculation of where the arrival point of the signal is changing. And so you'll get errors in your speed of sound measurement. Notice that the X on that photo in the middle there is not in the right place. It's not where the signal starts. It's off to the left a bit. And that's because the slope is so terrible there at the beginning of the signal. So tuning the transducers to the pipe is critical to get the proper wave shape. And as I said earlier, not all Lamb wave transducers are equal. Just because a company says that they have Lamb wave, they don't match them to the pipe. They pick them based upon the closest match to the wall thickness, but there's no frequency sweep done to further tune them to what the pipe actually resonates at. And that's a critical difference. So let's talk about an effect that's more relative to gas than it is to liquids, and that's high velocity. One of the things about gas is that we've already established that the speed of sound is much, much lower than it is for liquid. And so the sonic beam takes much longer to cross the pipe, which means that you're interfacing with the flow for a much greater amount of time. So for an equal amount of flow, you'll get 4 times as much delta time phase shift as you would on a liquid versus a gas. So a gas will get 4 times as much phase shift as a liquid for the same unit of flow. So you get very large up and down or time difference between the up and downstream signals. Whereas with liquids, it's very unusual for the upstream signal and the downstream signal to be more than 1 cycle separated. Or if I go back to the previous screen, each of these waves is of 1 cycle. So it's very unusual for the upstream and the downstream, and you'll see that in one of the next slides, to be separated by more than 1 cycle. Whereas with gas, it's very common. to be separated by multiple cycles. And then the other aspect of gas is that the flow velocity is much higher than it is for liquid. So what happens is the beam actually gets blown away from the received transducer. If you look at a wetted type flow meter, there's a potential to lose the signal altogether because the beam is collimated, shooting from one transducer to the other. And when you have a high velocity flow, it's pushing the beam away. And if it pushes it far enough away, you'll lose it and the meter just fails. With a wide beam transducer, although the beam still gets pushed down the pipe, it still arrives at the received transducer because there's so much energy over a wide area of the pipe that the signal is not lost and the meter is able to maintain operation. What you do see here, though, is that, for example, the blue trace is a zero flow condition. So the beam crosses the pipe and comes back, travels down the pipe wall to the receiver. But when there's a high velocity flow, it takes the red path and it's getting blown further down the pipe. So the pipe travel is less. And again, because it's not a dispersive beam, it has no impact on the shape. The shape stays constant. Just the amplitude varies. And the amplitude is really secondary. And I have a great example of that here. Well, let me just go here. So here's two waves that are phase shifted. So you see the downstream signal is in red, and the upstream signal is in blue. So the upstream signal is going against the velocity. It's taking longer to arrive. The downstream signal is going faster. And you could see 3 cycles of phase shift here. You can actually see it. It shows the delta time is 13.98 microseconds. The frequency code is 128, and I did the math on this the other day. Frequency code 128 is 250 kilohertz, which means that the period of one cycle is 4 microseconds. And so these beams are shifted by a little over 3 cycles, and there's your 13.99 time difference. So that would be typical of a gas. And many times gas, the up and down signals would be shifted even further. This is a totally measurable condition right here. 3 cycles of phase shift, only because of Lamb wave. Without Lamb wave, there is no way to do gas flow measurement. It would destroy a shear wave signal altogether. So looking at this condition a little bit closer, I'm just highlighting the transit time differential between the two, the up and the down. You could see 3054, 3068, that's in microseconds. So there's just under 14 microseconds difference. 1399, 1398. So here is a beam blowing condition. So if you look at this, this is what we call a correlated plot. So there's a slight difference here. If you notice up here, there's a button that says correlated and it's not checked. So you can see the differential between the two. In this shot, that button would have been checked. And what that does is it says to the device, put those two signals where they would have started from, which is they should be right on top of each other, the equivalent of a zero flow condition. And so correlation is how we can tell how many cycles of phase shift are occurring. So with them sitting right on top of each other, now we can see the difference between the two waveforms. You can see that the red one, which is the one that's traveling downstream and arriving faster, has higher amplitude on the back end, whereas the blue one has higher amplitude on the front end. And there's a differential. And this can throw a flow meter for a loop, because what can happen is as the beam gets blown, you can get a change in the correlation between the upstream and the downstream, which can cause flow measurement errors. And so to combat that, Controlotron developed something called beam blowing correlation, or it was called BB core. We've then changed it now, it's called HF, and it's built in to the 230, it's built into the old 1010 meters. What happens is, what we do is we look at the phase differential between the up and downstream signals on the beginning or on the first wave of the received signal. And then we look at the differential on the fifth wave, which is the end of the transmit. When we transmit, we send out 5 pulses, and those 5 pulses are what accounts for this buildup in amplitude. And then we stop transmitting, and then it falls off. So at the end of the transmit, we look at the same differential, and we calculate the effect of the beam blowing. And we apply a correction factor for it. And that eliminates errors that are potentially caused by a beam blowing condition. So, and this is a user-initiated automatic correction for the change that occurs in the signal created by beam blowing. And it's a very simple function. The user just goes to the menu location, selects enable for the beam blowing correction, or the HF, and then says do it, more or less. It just says activate. The meter does the calculation and sets the correction factor automatically. In order to do it, the 2 signals must be at least 1 cycle phase shifted from one another. So it can't be done at 0 flow. But if the flow is too low to actually do the measurement, do the correction properly, the meter will just tell you that, and it won't do it. But once the flow is established, then you can go ahead and do this beam blowing correlation correction. So just to kind of wrap up, finally, I reached this slide. Some of the differences, the real Siemens difference, are these factors here. Each of these was pioneered by Controlotron and Siemens. So many competitors have versions of these features now, but they weren't originated. Controlotron paved the road that these flow meter companies walk on now. And just a brief synopsis of them: Lamb wave transducers were pioneered by Controlotron. Transducers being tuned to the pipe's resonant frequency. Reflect transducer mounting for crossflow correction. Reynolds number calculation and correction. Multipath measurement. Pipe geometry correction or disturbed flow correction. Liquid ID, liquid correction, standard volume flow calculations, liquid tables, and high velocity beam blowing correction. Every one of these things are a part of a Siemens FS230 flow meter. Most, if not all of these, were pioneered by Controlotron. Excuse me. And as I said, many competitors have versions of these things, but not necessarily to the same level that we have them. So sorry for taking so long, but there you have it. Hopefully you got some questions answered, or may have questions regarding some of this stuff.
Well, John, thank you so much. I'm not surprised we went a little longer, because I've been fortunate to be in a couple of John's face-to-face training seminars, and you just get so deep into the weeds, which is great, because many times you just don't get there. But with John's experience, we're able to go there. So because of the time, John, we'll just ask that if anybody has any additional questions, feel free to reach out to John at his email as shown on the screen there, or you can send them to me, which is jimh@lesman.com. Of course, you can reach out to John. Siemens has a tech support number you can also call with any additional questions. I want to thank John for his time and his expertise, and I wanted to thank everybody for joining us today. So with that being said, I'm going to end the webinar and wish everyone a pleasant afternoon.
Okay, thanks.